previously we saw the error due to play, error due to friction and play, and when we added these two errors, that is the error in input signal from the friction, this is the error in input signal due to play in the rack and pinion mechanism. Now, since you have found out the total error in the input signal, now you have to find out what is the corresponding rotational error in the beta. For that, if you consider the whole instrument as one box, so from the what the instrument achieves, pressure to angular rotation beta. Now, this relation k, if you call it k, the gain, now you can write that equation in terms of maximum values of beta and P max, beta max and P max. So, beta max 80 degrees equal to 1.4 radians is equal to k times the gain of the whole instrument into 10 to the power 6 1 megapascal. So, from this we find out k as this. This is to change the delta P correspond to find out delta from delta P what should be the corresponding delta beta. So, delta P is this much we derived yesterday, that is 5 into 10 to the power 4 or 0.5 bar. So, delta beta corresponding to this, now substituting for k you get 0.07 radian. So, that is the corresponding angular rotation for an error of 5 into 10 to the power 4 Pascal. Now, for this rotation, this is the corresponding rotation for the least count. For the least count, we should have 1.5 mm as distance between two graduations. Now, if that is 1.5 mm for delta beta of 0.07 radian, what should be the pointer length? So, if L is the length of the pointer, then L comes out 21.4 millimeter. Previous class I did not have time, so that is how the length of the pointer is achieved. Now, we go to the next topic, uncertainty of measurement. Now, uncertainty is called error. Uncertainty is called error. Uncertainty, error, percentage of error, all these things represents only one term, uncertainty and error. Now, we have learnt in previously how the error is coming into an instrument through the elements of the instrument from atmospheric condition due to loading effect. This we know already. So, that means any instrument has got certain amount of error. Without error, we cannot measure a parameter. That means the real value, the actual value, true value, true value or actual value always remain unknown. There may be an instrument with very less error, but still there is some error. So, how to select instrument for a particular measurement? Suppose we want to measure the length of a table, working table. So, we use our ordinary scale. There may be an error of plus or minus 1 mm or whatever it is. So, there we need not have the accuracy in terms of micron, plus or minus 2 mm, plus or minus 4 mm, it is sufficient. That is not very controlling dimensions. We want to know the approximate dimension of the table, or so to say plus or minus 1 mm, it does not matter at all in this measurement. Whereas in bearings, if you take the bush bearing, bush bearing, we have got a bush. Within this, the journal is going to sit. And the clearance affects the functioning of the bearing. So, this is the clearance within the bearing, affects the functioning of the bearing. So, this is a functional area, functional dimension, and here it should be of the order of 0.001 millimeter. This should be the order, or 1 micron, 1 micrometer. This should be it should be measured with the accuracy of 1 micron dimensions. So, that means depending upon an application, we have to select an instrument with its tolerance or error. So, whenever we don't go always to an instrument which gives high accuracy, because the instrument is costlier. When you want to measure with high accuracy, instrument is costlier. Only when it is required, we go for such an accuracy. Otherwise, we use even rough errors are accepted in many types of measurements. While making a table, the length may be measured within plus or minus 5 mm. It does not matter if it is 1 meter. If it is 1.005, it does not 1.005 meter. It does not affect the functioning, the usage of the table. That is the selection of instruments depends upon the required accuracy in an operation. Then the next one is how the there is one more parameter in affecting the measurements, that is geometric dimensions. Geometric dimension. That is, when we say a rod is circular, how good it is, it may have lobed shaft, lobed surface, or it may have the elliptical in shape. So even though we are told it is a round, but realize in practice a round shape is very tough, because there are out of roundness, surface and surface irregularities. For example, you take a length of a rod, it's a round rod, length of a rod. So when you want to measure the length of the rod, because this is abstract geometric shape, but when we want to measure, we should ensure whether the two surfaces are parallel to each other, or the two surfaces, the end surfaces, circular surfaces, is it plane, or it has got ups and downs in its plane configuration, or it may have the surface may have the irregularities in terms of microns. So when we measure the length of the rod, we might have measured at see if it is slanting, the surfaces are slanting, we will have one dimension at the bottom, another dimension at the top. And if it is not plane, if it is having if it is having shallow and then the ups and downs in the macro dimension, then it depends where we put our measuring instrument. So even though we say it's simply length, but there are length, but actual length where it is, it's difficult to decide. So these are the abstract dimensions which may not be realized in practice. There are many error sources. So that's why we say in a measurement always error exists. So theoretical value always remain unknown, since any measuring instrument has got certain error. Now another point is, after using an instrument for a number of years, the calibration of the instrument might have shifted. So after usage of few years, that instrument requires recalibration. It requires recalibration to update the accuracy of the uncertainty, error, or inaccuracy. These are all analogous terms representing same phenomena. So we have to recalibrate the instrument, whether the manufacturer, whatever the error he claims, uncertainty he claims, still valid today. Or when we make an instrument for the first time, again the scale of the instrument is to be calibrated. For that purpose, we have got so-called calibration process. Calibration process. That is, in this process, we have to realize these atmospheric conditions, same atmospheric conditions in which the instrument is going to be used, or whatever we claim the error of the instrument will be within certain plus or minus 1% under the certain atmospheric conditions. Those conditions is to be realized for the calibration process. So temperature may be 20 to 40 degrees. Humidity may be varying between say 50% to 100%. So like that, atmospheric conditions are specified for any instrument in which it's supposed to be used. So for that purpose, let us consider a pressure gauge. This is a standard instrument. This is instrument which is going to be recalibrated, instrument under test, under calibration. That is, after realizing the atmospheric conditions for the calibration process, next we have to select the so-called standard instrument. The standard instrument should have an accuracy of 10 times more accurate than, that is, standard instrument should have 10 times more accurate than the instrument under recalibration, than the instrument under calibration. That is, if the instrument under calibration has got 1, 2, 3 bar like that as least count, the standard instrument should have 10 times more accuracy. That means it should be able to read, we should be able to read 0.1, 0.2, 0.3 bar also. So that's why we select a standard instrument. Now that is setup now is shown in figure here. That is calibration setup for a pressure gauge. we have the pressure source, fluid pressure, it may be a gas or liquid, and we have got a valve, pressure reducing valve, with which we can adjust any pressure downstream, and the same pressure is given to this instrument under calibration and also to the instrument under a standard instrument, where we can read where the least count is 10 times finer. Now the process is like this. We before that we have to write, suppose the true instrument reads up to third decimal of a megapascal, and if we completely close it, it is going to read 0, but we have to write 0.3000, because actually we can simply write 0 for this whole reading. 1 is 0, second is 0.100 or 0.1, but that is not permitted for calibration process. The 0 represent there can be some other number also. In this particular instant, they are all zeros. So you have to simply write all the terms as 0. Each term you have to write specifically 0. Even though if you write 1 0, that may be sufficient for mathematically. Mathematically sufficient, but not for measurements. So measurements, you have to write all these zeros. Now at that time you make some measurement. You make measurements. Note down in the standard instrument. Instrument, that is for increasing 0 onwards, we are going to increase. It shows already some reading, minus reading it shows. So below 0 it is there some reading. Note down. See, you find here in the instrument under calibration, we can read up to second decimal, and that means instrument for standard instrument should have 3 decimals. That is there already. So next we increase the we open little more and increase the pressure to 0.1. We are writing 0.100 because second and third decimal, the readings shown by the instrument is 0. So we write it 0.100. At that time it reads 0.06 plus 0.06. So plus is not written. So similarly we increase the pressure in steps of 0.1 megapascal and conduct this experiment until the standard instrument reads 1 megapascal. So at that time it shows the instrument test shows 0.99. This is what is shown. Now you have to take readings for decreasing the pressure. For that, don't start from this. You increase the pressure some more. Standard instrument should show some more reading than 1. That is 1.2, something like that. Then reduce the pressure from 1.2, and when it comes to 1, stop and take reading. At that time, it is 1.10. Similarly, reduce to 0.9, take the readings and complete it. That means you have got 22 readings. I can also write this also below this, but this way it is written, conventionally it is written. 1 for increasing, second decreasing. That means 22 reading, 11 into 2, 22 readings we have taken. Having taken these readings, this is the way of static calibration. Yeah? To do the static calibration, you have to take these readings, increasing the input in steps and decreasing the input in the same steps, and note down the readings. Next we plot these values in a graph, somewhat like this. So the x-axis is theoretical value, that is what is shown in the instrument, and the y-axis what is indicated, that is output pressure is from here. This is PT readings, this is PO readings, that is plotted here. So this red color or pink color represents the increasing, and decreasing readings are shown by yellow color. Now this is called best fitted line. This is best fitted line based upon the least square principles. That is, from the best fitted line, the points, the readings, the difference between the best fitted line and the readings, there is a different square of that reading, and add for all the readings, that will be the minimum of the squared of the differences of the points from the best fitted line will be minimum. That is the basis. To obtain such a best fitted line, we have got a formula to compute the slope and cut in the y-axis. What should be the cut in the y-axis? We have got, that is least square principles. We have got that equation. Suppose the equation is assumed as P0 is equal to MPT plus B. Yeah, this is the equation of the line. PO is equal to MPT, that is M is the slope of the line, and B is the cut, where the line cut the y-axis. So if this is the equation of the best fitted line, then M is equal to, in terms of readings, M is equal to N times, N is the number of readings. Here number of readings equal to 22, n is equal to 22 readings, n into sigma of pt into p0 minus sigma pt multiplied by sigma p0 divided by n sigma pt squared minus sigma pt the whole squared. This is m. To compute this, you have to have pt and p0 you can write in one line and multiply each individual one, call the pt into p0 term, add all those things at the end. That is the sigma of total of that. And then again open pt square, one column, square all these things, write pt square. At the end, yeah, pt square you find for each one, total will be the sigma pt, the total will be taken, that will be squared here. Pt square, sigma pt square you have to write it here, and sigma pt already we know end of it, total of it, that is square of it. So that is pt square, you will have separate column, n you find summation, that summation you put it and find out the value of m. Similarly, b is equal to sigma of p0 minus m sigma of pt divided by n. That means from this set of readings we can find out the slope and the cut of the line at the y-axis as b, and now the equation of the best fitted line is p0 is equal to, for the given set of readings, p0 is equal to 1.06 pt plus this minus value, b is equal to, b you have got a minus 0.05. So this is the equation of the best fitted line. That means whatever the reading you take in the instrument, corresponding value will be value to be obtained like this. P0 is equal to, this is the output reading. So pt you will get from this, p0 plus 0.05 divided by 1.06 will be the corrected value. That's the corrected value. For example, if p0 is equal to, so p0 is equal to 0.25 megapascal, that is the instrument, when we are using the instrument for to measure unknown pressure, that instrument gives a reading of 0.25 megapascal, then corresponding value of pt is equal to, so 0.25, that is p0 plus 0.05 divided by 1.06. So that comes about 0.28 megapascal. So 0.28 megapascal is shown as 0.25 in the instrument. So by using this equation we calculate pt, that is we say we will call it again, name it pc, that corrected value. For p0 the corrected value will be 0.28 megapascal. Yeah. Now next step is we have to find out what is the limit, error limit for this reading. Having found out the corresponding corrected value, we have to find out what is the error zone within which the instrument gives a reading. For that we have to use the phenomena, the standard deformation, standard deviation, that is sigma. This is what we have to find out from the, for a given set of readings, that sigma is equal to, if sigma is standard deviation, then sigma square is equal to 1 by n sigma of pc minus pt the whole square, pc minus pt the whole square, where pc is the corrected value. We have got corrected value for 0.25 as 0.28 megapascal, that is corrected value. pt is the corresponding true value. For 2.25 corresponding true value is 0.300, that is our true value. The difference between the two values, square and divided by 1 by n, that is the standard deviation. So for this set of readings, pc, now pc you can substitute, sigma square is equal to 1 by n sigma of p0 minus b divided by m, that is our pc, minus pt the whole square. So we open another column with this with the readings, where p0 minus b by m also is plotted, is also calculated and tabulated for each reading, and pt is there already. So from this we can find out the value of sigma. So sigma here it is obtained as 0.02 megapascal, 0.02 megapascal. By Gaussian distribution, if we take a limit as plus or minus 3 sigma, if you take the limit as plus or minus 3 sigma, then 99.7% of the reading, the error will be within plus or minus 3 limit, 3 sigma limit. So this is normally adopted. The error will put as plus or minus 3 sigma. So now the PT is equal to PC plus or minus 3 sigma. That way we go to, that is theoretical value lies between the limits of plus or minus 3 sigma from the corrected value. Corrected value, as we have found out earlier, this is the corrected value, P0 minus B by M. So here in this case, it comes to be PT is equal to 0.28. We have already calculated for one reading, 0.28 plus or minus 3 sigma comes about plus or minus 3 naught, that is plus or minus 0.6 megapascal. Now we find this is only true reading is 0.3, so that is within this limit. That is, it's varying between plus means 0.34 to 0.22. That is 0.3 is lying within this. That is, true value lies within this limit of 0.28 plus or minus 0.06. That is, so we arrive at the error of the instrument. That is, after recalibrating the pressure gauge, now we have got, we can specify the new accuracy of the instrument like this. True value, the corrected value should be found out by using this equation. That corrected value with the limit 3 sigma, then it gives the true value. True value, as always, it has a range within the 3 sigma limit. So that is our recalibration. Recalibration for a given reading, what should be the correct reading and its uncertainty. That is what we have found out now. Next one, what we are going to learn is the error in computed value. Error in computed value. Error in the computed value. We also say error propagation. When we have this problem, suppose in an engine, power is to be computed, power output or power input, okay, the efficiency of the engine. Then you have to measure the flow rate of the fuel. Then you have to measure the power output in the shaft in terms of torque developed in the shaft and the rotating speeds. So 3-4 measurements you have to make in order to find out the power efficiency of an engine. So from the measurements we have made, 3-4 measurements, we are going to compute a value. And we also know any measurement has got its own error zone. Now, what is the error of the computed value? Obtained from the different measurements having different inaccuracies. That is why we say the computed value, how the error propagates into the computed value. That is error propagation into the computed value. That is what we want to find out. Yeah? The computed value will have some error based upon the error of the individual measurements. And first we derive the mathematical equation for this phenomena. Suppose Q is a computed value obtained from the calculation of obtained from measurements of x1, x2, and so on xn. N measurements are made, and using a function q is equal to function of this, we can compute the value of q. Now the error, each one will have, each measurement has got an error of x1 plus or minus delta x1. The x2 will have x2 plus or minus delta x2 and so on. So the computed value will have error zone of delta q is equal to function of x1 plus delta x1. I will write the square bracket, and x2 plus or minus delta x2 and so on until xn plus or minus delta xn for that last nth instrument. So that is the error in the computed value and its error. Now we want to find out the magnitude of q, delta q. So we simply omit one of the signs. So we can also write q plus delta q is equal to function of x1 plus delta x1 and x2 plus delta x2. So omitting one of the signs, we can write it like this. Now we expand that right hand side by using Taylor series. By using Taylor series, you can write is equal to function of x1, x2 up to xn plus plus delta x1 into dou f by dou x1. Yeah, this is delta x1 term plus delta x2 into dou f by dou x2, like that, plus half of delta x1 square into dou squared f by dou x1 and delta x2 square into dou squared f by dou x2, and so on. It goes for the second second derivative, and then plus 1/3 of the delta x1 cube, and so on. It will be a Taylor series will be expanding like this. Now if you reduce, now you find this here you got q plus delta q, and we know q is equal to function of x1 x2. So both sides you have got this is equal to this, you can cancel. So delta q is equal to this plus this, and we know the error is going to be a small quantity. When it is small, delta x1 square, this square term you can neglect it. So this also will go away. Finally, delta q is equal to, considering only the magnitude of each term, delta q is equal to delta x1 into dou f by dou x1, consider only magnitude mod, total error we will find out, into delta x2 into dou f by dou x2 mod, and plus like that dou xn. So n instruments, dou f by dou xn. So this is the total error, that is the error in the computed value obtained from the individual measurements, n measurements. Now this equation assumes that all instruments are working with the maximum error. Then what is the maximum? Later on we are going to put q is equal to q plus or minus delta q. So that is plus, so this we will get some value, that is plus or minus you are going to put always. That plus value when you take, that is individual instrument itself as that is q maximum, q maximum. So we will say q maximum is equal to q plus delta q. So q minimum q minus delta q, that is these limits are suppose we take the plus limit maximum value, that is each instrument is assumed to work simultaneously at the maximum limit, and then you will get the delta q, maximum limit for the q. Similarly, the minus sign, you know, that the negative side, all the instruments are supposed to work in negative maximum, and you will get it. But such an operation, see, when one instrument measures with maximum error, another instrument need not measure at maximum error. So this equation gives a very wide limit for the computed value. Say the instruments may not be working simultaneously at the maximum level or minimum level of the error. So to get a realistic view, we have got so called by using the principle root sum square, by using the root sum square, we get this equation delta q is equal to root of delta x1 into dou f by dou x1 whole square, plus that is individual instrument error component is squared, and then find the square root. So delta x2 into dou f by dou x2 whole square, and so on up to n term, all these things. So this is the realistic limit. That is, if you have found out the delta x1, delta x2 as plus or minus 3 sigma principle, which you have learned under the calibration process, then this delta q also correspond to 3 sigma limit. That is more than sufficient. 99.7% of the readings will be within this limit. So that is the understanding. So we will use this equation always to find out the error propagation of the computed parameter. And suppose we have a measurement to be made. Okay, I think suppose we have a measurement to be made, and the error of the computed value, if it is given, suppose delta q should be within certain limit, then what are the type of instruments, the error zone, the error limit we have to select to obtain a particular error in the computed value. If that is given, that means we have to select based upon the error in the computed value, we have to select individual instruments, and for that there is infinite number of procedures to obtain it, methods to obtain it, but we will follow one method, that is, we will say the component of error contributed by each measurement is equal, that is this one, from the first instrument, this is the part contributed by the first instrument, error contributed by the first instrument towards delta q. We assume the component of each instrument is same. That means if n measurement is there, then n into this root of this will be giving rise to delta q. Under that assumptions, that is the equal error portion is given by each measurement, then we can easily find out what should be the error of individual measurements. So now we get, that is delta q is equal to root of n times dou f dou x1, for example, dou f by dou x1 whole square. That is what we have got, and assuming delta x1 dou f dou x1 whole square is equal to this. So n instruments are there, so like this, and then this gives rise to, that is under the assumption delta x1 into dou f by dou x1 is equal to delta x2 into dou f by dou x2 mod. They are all equal. Under that condition, we write the above equation. Now we can obtain the, suppose instead of 1 you call I, where I will vary to 1 to n, I is equal to 1 to n, you can write 1 to n. Then we can find out what should be the delta xi. So delta xi is equal to, from this we can easily obtain delta xi is equal to delta q divided by root n. This root n comes, this is square will be under the square root, it will be same value, dou f by dou xi, dou f by dou xi. That is, this gives the form equation for selecting instruments for obtaining a particular error in the computed value. So now we have to now we can work out some example also how these equations are made use of. Before we learn how to use those equations, it is important we know about something about significant figures and rounding off. This is very important in the sense, suppose we use one time a very precision instruments, another time a rough instrument, a very rough instrument, and if you add suppose two stretches, suppose we want to find out the length of the line, for up to this we have used one instrument, and from here another instrument, and if they have different inaccuracies, then you cannot simply add those two numbers, because the rough instrument what you have made use of, it has eaten away the accuracy of the bad instrument or accuracy of the good instrument. So final measurement will be accurate only to the accuracy of the rough instrument. That is the basis for this. So how to do scientifically, that is what you have to learn. For that, what is significant figures and rounding off is to be understood. Suppose you take a number, suppose some number 2058, some number, it's a whole number. So here we say each number here is significant. That is 0, which is within a given number, is significant. But 0 will not be significant in some other instance. Suppose we write 0.0045 like that. Then 4, 5 are significant, and 0, 0 are used only for fixing the decimal place of the significant numbers. In that case, the 0, 0 is not significant. Suppose if we write 2.00, so just like some reading in our calibration measurement, calibration process, we have written there 0, 0 to indicate there are supposed to be readings in a particular measurements, they are 0. To indicate that, you have to write 0, 0, so that we know the instrument is measuring up to second decimal. So here 0, 0, even the value is 0, but it represents something, so they are significant. So here it is significant, here also it is significant. In this place 0 is not significant, and in another place is 0, suppose 2700. So this if we write 27 into 10 to the power of 2, then in this number we are interested only how many hundreds are there. That means only 2700, 27 only important, the 0, 0 are not important. Suppose we write 27, same number we can write 27.0, 27.0 into 27.0 into 10 to the power of 2. This number can be written like this also. So in this case, 1 0 is here important. 20 up to 1 decimal we are finding out. So out of this, 1 0 is significant, second is not insignificant. But if you write 0 in 10 to the power of 2, here all the zeros are significant. That means zeros can be sometimes significant, sometimes need not be significant. Here if you write 27.00 in 10 to the power of 2, it is both of them significant. If you write 27.0 in 10 to the power of 2, only one of them is only 0 is insignificant. If you write 27 in 10 to the power of 2, both the zeros are not significant. That means there are two instances where zeros are significant, two other instances where zeros are not significant, but all the numbers 1 to 9 are always significant, always significant. This is the concept of significant numbers. 1 to 9 are always significant. 0 is sometimes significant, sometimes it's not significant. That you have to understand under the context, under different context. If it is entrapped within numbers, then it is significant. And if it is used only for fixing the decimal place, it's not significant. And a number like this, when it is written in a particular fashion, sometimes significant, sometimes it's not significant. So that is concept of significance. Now rounding off. Rounding off of a number, a given number. Suppose a number is there, a given number. How the rounding off is done? Suppose we have a number, so 4.345356. Suppose we have got a number like this, and we want to round it off to now how many decimal places? 1, 2, 3, 4, 5, 6 decimal places are there in this number. And suppose we round it off to a particular decimal place instead of instead of 6, it is sufficient if I have only third decimal place. Then how to do the rounding off? There is a particular rule. Look at the number that is being discarded. Now 356 is discarded. If it starts with a number greater than 5, if it is greater than 5, number greater than 5, add 1 to the desired decimal place. So in this case, this rate comes to 4.345. But because this number is less than 5, and leave the number as it is, so we left the number as it is. If it is greater than 5, suppose we want to have 5 decimal place. Now it is 4.3453. Now it is greater than 5. Discard a number, starts with greater than 5. Add 1 to the desired decimal place. Now it is 36. That is for the fourth decimal place. If it is less than 5, we leave the as it is. That is 3453. 5 alone. Suppose we want only 3 decimal places. The neglected number starts with 3, so leave the decimal place untouched. Yeah. If it is greater than 5, add 1. If it is less than 5, leave it as it is. Suppose it is exactly 5. That is exactly 5. Now it is up to second decimal place we want to fix, and we find the discarded number starts with 5. And how to round off this number? Now look at the desired decimal place. That what is the number 4? If it is even number, leave it as it is. So 4.34. If it is odd number, then add 1 extra. That will be the case. This one I will use a different chalk. Suppose this is the place. Suppose I want to leave it with 4 decimal places. Round it off to 4 decimal places. Then we find the neglected number, discarded number starts with 5, and desired decimal place has got an odd number. So this comes to, for this the number rounded off number will be 4.3454, because even odd number is increased to next higher even number. So this the rule. There are 3 points. The discarded number, if it starts with a number higher than 5, always add 1 to the desired decimal place. if it is less than 5, leave the desired decimal place as it is. If it is exactly 5, discard number start with 5, then add 1. If it is a odd number, leave the number as it is. If it is an even number, desired place, decimal place, if it is even number, leave it as it is. That is how the rule is adopted for a rounding off of a number. Now, what is the rounding off procedure for computations? For computations, how many computations we have? Addition and subtraction and multiplication and division. Multiplication and division, there are only one rule for both of them, and division. These are the three basic mathematical functions we have. And what are the additions, what are the rule for rounding off for computations? So first we will see for the additions. Suppose we have some 5 numbers. So 3.745, 0.8, 0.8, and then 2.637, and then 0.8356, and then 1.452. So suppose these are the numbers to be added. What is the rounding off procedure? First point is, note down what is the least accurate number. That is the one which has got least number of decimal places. This is the least accurate number. This is our least accurate number. This is least accurate number. Note down the number of decimal places and round off all the other numbers to the next decimal place. So from here, what we get, next decimal to second decimal place, we have to round it off. So when you round it off second decimal place, it comes like this, 74, because 5 is discordant number and desired place is a odd number, even number, so leave it as it is. Then 0.8 as it is you write, then 2.63 we have to write up to 3, but the discordant number is more than 5, so 2.64. That is a rounded off number. Now we have to, now up to 83 we have to have, so discordant number starts with 5 and is odd number 3, so make it next higher number 0.84. And then here the discordant number is less than 5, write it as it is up to that place 4, 5. Now add this total, so 9.47, and round it off to the same decimal place as the least accurate number, and from here we have to reduce to the same decimal place as the least accurate number, so 9.5, because discordant number is greater than 5, so add 1 to the desired decimal place, so it comes 9.5. So this is the rule you have to adopt for the addition. For subtraction, suppose you have got two numbers, 8.7456 minus 0.142. Subtraction involves only two numbers. Addition can be any amount of numbers, but here only two numbers. Rule is simple. If they have got different number of decimal places, identify the less accurate number having less number of decimal places. Round off the other number to the same decimal place, and then subtract it and leave it as it is. So here we have got second number is less accurate. So round off the first number to the same decimal place up to here third decimal. So that means 8.746, because 6 is higher than 5, and add 1 always. So minus 0.142. So the answer will be also same number of decimal places, 068. So this is the answer for the subtraction. Rounding off procedure adopted for subtraction. Suppose multiplication division, we have got this, that is 2.3 into 7.446 into 0.0083 divided by 4.2526. Suppose this is the computation we have to do, and how to round off the final answer. Here you use the concept of significant figure also. Up to this, that is addition subtraction, we have not used the significant figures, concept of significant figures, but here you have to use the significant figure. Find out what is the least accurate number in this multiplication division. Find out the number of decimal places. Find out number of the significant figures in the least accurate number. Now 2.3 is one which is having the least number of decimal places. So it happens to be the least accurate number. Least accurate number. Next is number of significant figures. Here it is 2 significant figures, that is here it is 2. And so round off all the other numbers to one more significant figure and write the computation again. That is one more significant figure means up to 3 significant figures. So now I will write it 2.3. Here we have got 4 significant figures, all numbers are significant. So we have to have only 3. So it has to be left somewhere here. 6 should be left. So that is, it is giving rise to 7.4 because 6 is higher than 5. Add one number 5 into here only 2 significant figures. We write it as it is 83 divided by here 3 significant figures. So 2 6 we have to leave and is smaller than 5. Write it 4.25 without any modifications. And compute to the number to 3 significant figures. That is now obtained as 0.0335. That is we have got 3 significant figures. And then reduce this answer to the same number of significant figures as the least accurate number. That is, we can now here we got 3 significant figures in the computation. Reduce to have the same significant as the least accurate number, only 2. This gives rise to 0.003. This we are going to make like it is exactly 5. This odd number, make it a next higher even number. So this is the answer. That is how we have to find out the use the concept of significant figures and rounding off for individual numbers as well as for the computation of all these things.